Okay, so till now this is what we have seen, right? So this is my input signal, the Vin, and the red color is after the full wave rectified output being filtered by the capacitor. So after the full wave rectifier, it was something like this, right? It was something like this. Okay, and of course after getting filtered by the capacitor, it has become this waveform. We have got this waveform, the red color one. Okay, this is my original input signal, the Vin, and the red color one is after the filtration by the capacitor. And also we have seen in the last discussion that the ripple voltage or this BR is very much dependent on the capacitor. Higher the value of the capacitor, lower will be the ripple. But the consequences of increasing the capacitor is that it will increase the diode current and it can spoil the diode. So we need to get another approach to make this flat, right? This is not yet DC, still there this pulsating is going on. So we want to make it flat. Okay, so this can be achieved by just chopping off this whole waveform. So if I can somehow chop this whole waveform at some value, okay, so at some value, maybe this, let's call it as this peak value after the, maybe if it is supposed maybe at 9 volt, right? So we can chop it at a lower value, maybe at 6 volt, right? And we can get a plain DC. So this is what we are going to do, right? So we are going to do this kind of chopping using a Zener diode. So this process is called Zener diode voltage regulation. Okay, so where we are trying to chop it. Okay, so we will discuss this thing in details in today's class. So the topic of today's discussion is voltage regulation by Zener diode. Okay, so what exactly it means? What basically, let's understand what is this Zener diode. Okay, so if you remember when we discussed about a diode, we discussed about the breakdown phenomena that is happening in the reverse bias region. So let's go back to the discussion of the diode's characteristics. So this is my ID VD curve of the diode. This is in the forward bias region. The current is increasing exponentially. And if you remember in the reverse bias region, there is this current IS, and if you make this VD very, very negative, then what will happen is at some point of time, it is going to break off. So at some point of time, this is going to break down, okay? And this is called the breakdown region, okay? And this is also sometimes called as the Zener effect, and we are going to use these phenomena, okay? So at some voltage, right, at some voltage, maybe let's call it as this is also called as minus VZK. So at a voltage, reverse bias voltage of ZK, which is also called as the knee voltage, okay? So my this VZK is the knee voltage. So this is the voltage where the suddenly the diode in the reverse bias region will start conducting huge amount of current in the reverse bias region, okay? And you can see that at this voltage, maybe there may be a slight increase in the current, okay? And this current is called, the current corresponding to this VZK is minus IZK, or this is called the knee current, okay? So after this voltage, the diode is going to be in the breakdown region and it's going to become very sharp, okay? So what it means is that this kind of effect is called the Zener effect, and this kind of diode, right? So by selecting a proper doping concentration, this knee voltage can be made very small, maybe 6 volt, 7 volt, okay? So that means here what it means is that this voltage is going to become almost constant, okay? And if I can make sure that this current is not going beyond some maximum value, so if I can make sure that this is not going, beyond this Imax value, then this is a reversible process. I mean, my diode will not be, even though it is a breakdown, the property of the diode will not be affected. Okay, I can still reuse it. But if it cross maybe this Imax current, and then I should say that there's a possibility that the diode can be spoiled. So this kind of diode, which is used in the reverse bias region, is called the Zener diode. Okay, and it is represented by this symbol. The symbol is like a diode, but only here we have these two separate legs. Okay, so this is a Zener diode and it is used in the reverse bias region. So what it means is that if it is, suppose it is breaking, right, the breakdown is happening at around 6 volt, then what will happen is you can see that it is almost like a constant voltage, right? It's almost like a constant voltage, and this phenomenon, if we can make sure that it is, the current is not going beyond Imax, then we can use this phenomenon to uh, implement voltage regulation. So what I mean is, if I have a full wave rectifier, right, and full wave rectifier, and if I can connect this Zener diode in the reverse bias region, right, okay, so this will give a constant voltage. Okay, but then here we have to be little careful in the sense that, suppose in this case, this is after the full wave rectifier with filtering, right, and we are going to connect with a a Zener diode whose breakdown voltage is near around 6 volt. Okay, but then if you see here, because I'm applying a huge amount of voltage, right, maybe at 9 volt, so you can see here a huge amount of current is going to flow. So if I increase this reverse bias voltage in this direction, right, a huge amount of current is going to flow. So this can easily damage these Zener diode. Okay, so to do that, we have to add a resistor in series. This resistor R is going to limit the current. So if a huge amount of current will flow through this R, so there will be a significant voltage drop across this resistor, and then this will stop, or this will prevent this Zener diode. So we need to do a proper analysis of this one. Okay, so let's discuss this one in more in details. So the knee voltage can be varied by varying the doping concentration of the PN junction. Okay, so this is the complete model. Okay, so this is my full wave rectifier, and I have this capacitor C for filtering, and then I have this Zener regulation. So this is going to give a constant voltage across these two nodes. It will be in the reverse bias breakdown region. So I just need to make sure that this voltage is higher than the knee voltage, so that this is always in the breakdown region. At the same time, I have to make sure that this R is large enough that the current flowing through this, right, is not exceeding the Imax, right? Especially when there is no load, right? Suppose if I'm not charging my phone, so my RL is infinite, right? So my R is infinite. At that time, all the current is going to flow through these Zener diodes. So I have to make sure that I need to select this R such that this current flowing through this is lesser than Imax. So these are the different things that we are going to analyze. So for that, we need to model this one properly. So we need to make a proper model of this Zener diode before we start analyzing it. Okay. Okay, so let's try to focus on this region and try to model it properly. So if you see here, I can approximate this thing by easily by a straight line. Okay, so what I will do, I will select maybe a test point here. Okay, so and I'll try to find the slope. Okay, I'll try to find the slope of the line which is passing through this point. Okay, so yes, I have approximated this with a straight line. Okay, and it is passing through this point. Okay, and of course if you see this point, this is intersecting here maybe at a value which is maybe, let's call it as I ZT. Z stands for the Zener diode and T for the test current, and then maybe this one is at some, this is um, minus VZT. Okay, and then I have my straight line. Okay, and this straight line is intersecting this x-axis at, the straight line is intersecting this x-axis maybe at minus VZ, is intersecting this x-axis at VZ0. Okay, so now what I can do is, so I have approximated this whole thing with a straight line. Okay, and it has intersected this one. Okay, and of course we can find out the slope of this line. Okay, so we can find out the slope of this line, and we know that the slope of this line, which is basically, if you see the slope of this line is, you see basically it is basically the delta ID delta VD. Okay, so we know that delta ID delta VD, we can call it, this is uh, inverse of the resistance. Okay, 1 by R. Okay, or 1 by RZ. So the slope is basically, this is the slope. Okay, the slope of this line, slope of this green line, or the slope at this point is given by 1 by RZ. Okay, the slope of this line is given by 1 by RZ. So let's again just draw the approximated this straight line. So this is my final approximation. Okay, so this is intersecting at minus VZ0. Okay, as shown by this one, and the slope of this line, okay, is 1 by RZ. Okay, so if we write this simple equation, y equal to mx plus c, we'll get this line equation. So we know this y is id, and m we know that it is 1 by rz, and x is basically vd, and of course c we can find it out. Okay, so c means basically when my id is 0, when my id is 0, so my vd will be equal to minus vz0. So when id is 0, my vd is equal to minus vz0. So if I substitute this one here, I will get c as I will get c as vz0 by rz. So if I just substitute it, what I will get is, I will get my vd is equal to, I will get vd is equal to rz id minus vz0. Okay, so this is the equation that I will get. So now this was the equation when we considered that I have a, so this was the equation when we have a considered as a diode, and we have considered this diode where the ID is in this direction and my VD is positive negative. Okay, but now if you see the Zener diode, the current through the Zener diode is going to go like this, right? So reverse bias current, and then this will be at higher potential compared to this, because it is going to get used in the reverse bias region. Okay, so that's why for Zener diode, we need to reverse the polarity of the ID and the VD as well. Okay. So for this is Zener diode, and this will be reverse. So IZ will be in this case IZ. So the current flowing through this Zener diode is called IZ. Z is used for the Zener diode. D is for the normal diode, and this will be at higher potential compared to this VZ. Okay. So what it means is that the my ID is reverse, and this VD is also reversed to VZ. So for Zener diode, my IZ will be equal to minus ID, and my VZ will be equal to minus VD. Okay, so we are just trying to reverse the polarity so that things become simplified. Okay, so now once I substitute this one, right, VD will be substituted by minus VZ, and ID with minus IZ. Okay, so therefore what I will get here is, if I substitute this value, minus Vz will be equal to Rz minus Iz minus Vz0. So this implies that my Vz is equal to Rz Iz plus Vz0. Okay, so for Zener diode, my Vz, the voltage across the Zener diode, is given by Rz Iz plus Vz0. Okay, so what does this equation means? This equation means it is as if I have a resistance here and a voltage source here. Okay, so if the current flowing through this branch is Iz, and the potential developed across this is Vz, and this is my Vz0, this is Rz, and the current flowing through this is basically Iz. So this is what this equation represents. Okay, so what it means is that my Zener diode is supposed to have a constant voltage, which is ideally it should be just a constant voltage Vz0, but because of this small slope, there will be a small component of the resistance, and as the current increases, this slope will take care of the slight increase in the voltage. Okay, so this is what it means. Okay, so this slope is capturing the increase in the voltage from the knee voltage, or the Vz0, which is close to knee voltage, and this slope, or the Rz, is capturing this one. Okay. So again, here also, if the current increases, the drop across this Rz increases, and this will take care of the slight increase in the voltage with increase in the Iz. So this is the model of my Zener diode, and with this we can now start solving the Zener diode problems. To understand this concept more clearly, let's consider an example. So this is my full wave rectifier, and of course this is coming from the transformer. Okay, so this the step down voltage is applied here. Okay, and then finally, after the full wave rectifier, I'm having the rectified output here, and let's connect to this ground. Okay, and now here I'm supposed to find out the value of R and the value of RL as well. Okay, so let's give some value to this Zener diode. Okay, and then accordingly we'll solve this problem. Okay, so for the Zener diode, okay, Rz is equal to the resistance Rz, this, right, the slope, this, right, the inverse of the slope is equal to 10 ohms, add a test current of IZT is equal to 10 milliampere and VZT is equal to 6.3 volt. Okay, so what it means is, if I consider this point, right, IZT and of course minus IZT and minus VZT, so here if I evaluate the slope, or the inverse of the slope will be RZ. Okay, and of course Imax, right, the maximum current in the reverse bias region through this Zener diode is given by 50 milliampere. Sometimes it is also represented, the symbol is IZM may be used, right? The current through this Zener diode, the reverse bias current, okay? So this symbol is also sometimes used. Okay, I think better use that symbol. Let's change here also. Okay, so now these are my values, okay? So now we can use our equation and we can find the VZ0. So we know, right, VZ is given by VZ0 plus IZRZ, okay? So substituting these values implies VZ is equal to 6.3 volt is equal to VZ0 or VZ0, and IZ is, in this case it is 10 milliampere into 10 ohms, okay? So if I just find it out, it becomes VZ0 is equal to 6.2 volt, okay? So now let's replace this one with the model that we have, the model which represents this equation. Okay, so this is my this is the model, this is my R, this is the model of the Zener diode, okay, and of course this is the load resistance. And if you see the waveform that is applied here, the rectified waveform after filtering, okay, so B rect, okay, so the B rect will look something like this, okay, and of course here it should be supposed to be DC, plain DC, and this is my, let's call it as V out, let's call it as V out, okay. Okay, so now if you see here, this will have a maximum voltage, okay. So so let's call it maybe, it may be 10 volt. We still don't know this one, okay, because this will be defined by the resistance, right? Because there will be this surging in this resistance in this part, so this will be defined by this one. So we still don't know this one, so we will see what is this value, okay. So yeah, so now first step is to find out this R, okay, to find out this R. So this R is basically, what is this R doing? This R is preventing this Zener diode. We don't want to make sure that the current flowing through this is always lesser than IZM, the maximum current allowed through the Zener diode. So the maximum current will flow through this one when there will be no current through this resistance, okay. Otherwise, in every time this current is going to get shared, right? The current flowing through this resistor is going to get shared. So if you call this current flowing through this IL, current flowing through this one as, okay, and of course the current flowing through this is IZ, okay. So to find the minimum value, we should consider that this IL is 0, okay. So all the currents are flowing through this Zener diode, okay. So to find the minimum value of R, we need to consider that the load current is 0 or RL is infinite, okay. That means I have not connected any load. Okay. The other thing is the current through this will be maximum when this Vrect, okay, when this Vrect is at its peak, okay, at its peak value. So here, of course, the current will become smaller, but when this will be at the maximum, so it will be the current, this Iz is going to be maximum. Okay, so now what we can write is, what can we can write is, okay, and the next thing is, okay, so now we want to find out the, so now suppose it has increased and, suppose this is at, there is no load current and this is at maximum value and the Iz has gone to the maximum value. So the V out also will become maximum. So the V out is basically the Bz itself. V out is nothing but Vz only. Okay. So we also have to find out the maximum voltage, corresponding to this maximum current. Okay. So therefore Vz max or is equal to V out max will be equal to Vz0 plus Iz max into Rz. Okay, so basically it means that plus Izm, right, Rz. So this is 6.2 plus this is 50, right? 50 into Rz is 10, right? 50, this is milli ampere, okay, 10, so it is around 6.7 volt. Okay, 6.7 volt. Okay, so now what I can write is, the current flowing through this. Okay, and the current flowing through this, the Imax, right, the total current flowing through this, which is basically the maximum current, Izm, we can rewrite with the Vrect. We can find out this resistance such that this voltage is never beyond this maximum voltage. Okay, so therefore my Izm is equal to, the maximum current is Vrect. This also should be maximum minus the V out Vz max by the R. So Izm is equal to this B rectified maximum minus the Vz maximum or the V out maximum by R minimum. So if I just rearrange this equation and substitute the values, what I'll get here is max is, we know that it is 10, and Bz max is, we know that it is 6.7 based on whatever we have calculated, and Izm is the 50 milliampere. Okay, so therefore my R min 66 ohms. So therefore my R should be always greater than 66 ohms. Okay, so of course, just taking only 66 ohms may not be good. So we need to take something which is higher so that we can make sure that it never goes to 66 ohms, because what will happen is there will generally, if we are given a resistance, there will be some tolerance value, right? So plus minus some value. Okay, so if I'm given a resistance maybe 66 ohms, there will be plus minus 5% or 10% tolerance, and at the same time what will happen is, due to the aging, the resistance can also vary. Okay, so for this example, let's consider this R to be 80 ohms to be on a safe side. Okay, R to be around 80 ohms. Of course you can take lower also, but to be on safe side, it's better to take always in a higher end. Okay, if you're not very sure. Okay, let's consider higher side, 80 ohms. Okay, so now once we define this resistance, okay, so this will define the minimum value of this RL. Why? Because if my this RL is too small, right? If I make this RL like if I almost short it, maybe like 0 ohms, then what will happen? There will be no voltage drop across this Zener diode, and it will be no more in the breakdown region. Okay, so that's why there is a minimum value. Okay, so it should not be too small. So this defines the minimum value of the load that I can connect. Okay, so of course, the open condition, we have made this infinite because we want to find out the maximum value of, we want to find out this R, and it doesn't exceed the maximum value, and it is required to find out the RL equal to infinity, because most of the time we may not be use this charger or this voltage source, because ultimately we are using this as a charger or a voltage source to charge some battery or to operate some electronics device. Okay, and many of the times it may be possible that we may not connect our phone for charging and all, so the RL is infinite, so that situation is valid. At the same time, we have to define what is the minimum value of RL, like what all it can support, right? Which all devices can support, right? So and this will decide once we define the minimum value of RL. This also will decide how much power it can provide. Okay, because once we define, because this V out is approximately, it will be around 6.3 only, 6.3, 6.4, right? And once this is like, because this V out is almost fixed, so once we give the value of RL, the power also will be fixed, right? The power it can provide, this can provide. Okay, so yeah, so now we have to find out the minimum value of RL, and of course we'll see that this RL will be in 100 of ohms, and if you see here, this is in few tens of ohms, right? So, and this has become, you have taken it as, this, in this case it's 80 ohms, and this will be, you will see that it will be usually more than 200 ohms, or what I mean here is that why I'm writing this value is that this is much larger than this RZ. Okay, so what is going to happen is, if I see the impedance, right, the impedance that is seen by this capacitor, because this will define the lower value. Okay, so because this capacitor C is going to discharge, okay, and the RC time constant is defined by the resistance of this network. So the resistance of this network is going to become this R plus, if you see the resistance seen in this direction. So the resistance that is seen in this direction is basically the RZ parallel RL. Okay, so this is the Thevenin equivalent resistance. Okay, this will be the RZ parallel RL. Okay, so so what it means is that the impedance looking through this is approximately R plus RZ parallel RL. And because my RZ is much smaller than RL, okay, because as I was mentioning, this will be more than 200, right? So that means we can approximate this whole thing with R plus RZ. And okay, so the discharging time, so it is mostly defined by R plus RZ. Okay, so yeah, so this will be defined by the C and R plus RZ. So what it means is that once you have selected the value of this R, this voltage is going to get fixed. Okay, so the lower voltage is going to get fixed because it is not dependent on this RL. It is, or even though it is dependent, the dependence is very less, because the overall resistance impedance that is looking here is RZ. Okay, so so this is going to get fixed. Okay, so in this situation, based on the simulations, what I have seen is with this value, this will be around this will be around 8 volt. This will be around 8 volt, considering as C to be 140 microfarad. Okay, yeah. Okay, so now this is done. Okay, So now the thing is we are supposed to find out the RL minimum. Okay. So the maximum value of RL, we know that it is infinite because that's the no load condition. But this is the minimum load that I can apply. Okay. Or the it is also sometimes called it the maximum load because the current flowing through this will be maximum when this RL is minimum. Sometimes this is called the highest load. Okay. So now in this condition we are supposed to find out the RL. Okay. So now so what we want to find out this RL minimum, we just want to know when this has just started breaking down. So basically what I mean is that the current flowing through this will be minimum. Okay, so as small as the just the knee current IZK. Okay, and it has just started breaking down and this IL is maximum. So basically we want to know this situation. Okay, so my V out will be equal to VZK, and here what we'll do is we'll approximate to VZ0 because this VZ0 and VZK are very close. So VZK can be approximated as VZ0. Okay, and my current has just reached the knee current. So in this case the knee current is given as 0.2 milliampere. IZK is 0.2 milliampere in this problem. Okay, so what I mean is in this case my V out is equal to VZK, which is approximately equal to VZ0. Okay, and current flowing through the Zener is IZK. This is the minimum current that is flowing through this. Okay, IZK current is flowing through this. Okay, and of course yeah, so these are the two conditions. Okay, so therefore my current flowing through the load, okay, because now V out has become VZ0, so the current flowing through this IL will be equal to V out by RL definitely, and V out we know that this VZ0 RL. Okay, and now in this case to find out the minimum RL, we are considering that this should be in breakdown. Okay, so now if you see the rectified waveform, this will always break down when the voltage is higher, but it can stop breaking down only when the voltage is lower. Okay, so to find out this RL minimum condition, we need to consider this minimum voltage. Okay, because if we know that this is diode or Zener diode is breaking down at the minimum voltage of this one, definitely at a higher voltage it's going to break down. So we need to consider the Breg minimum, because we need to consider Breg minimum because if okay, so we need to consider the Breg minimum because if it is breaking down at this voltage, it will definitely break down at higher voltage. Okay, so now therefore the current flowing through this resistance. Okay, so the current flowing through this resistance, so which is basically the IR, will be the summation of these two currents. So here current flowing through is IZK and the current flowing through is IL. Therefore IR in this condition will be IZK plus IL, and this is basically the current flowing through this is the Vreg minus this will be in the V minimum, so which is VZ0. Okay, so Vreg minimum minus VZ0. Okay, and of course the resistance R. Okay, so what you can do is IZK we know that is 0.2 milliampere plus this IL is basically again VZ0 because the output is VZ0, and of course this RL again we have got from here is equal to Breg minimum. In this case it is 8 volt. Okay, and VZ0 is, we know that it is 6.2. Okay, and this R is we have considered as 80 ohms. And if we just evaluate, right, again we can make this VZ0 also as 6.2. So basically 6.2 by RL will be equal to, or therefore my RL, this leads to RL 278 ohms. Okay, therefore my RL should be always greater than 278 ohms. Okay, so this concludes the calculation of the R and the RL. Okay, this is my LT-Spice setup. Okay, for this for this voltage regulation with the Zener diode. So yeah, let's set the value. So I already have drawn this circuit, and I'll be sharing this one in the website as well. This LT-Spice file. So we have considered to be 80 ohms. Okay, so fine. So okay, the resistance is 80 ohms. Okay, so let's consider the first case when this is really very high. So let's consider 1 giga ohm. So it's like as if open, right? The R is very large, it's infinite, it's not affecting this one. So we want to see this behavior of just this Zener diode. Okay, so just run the simulation. Okay, so if I just plot here, you can see here this waveform. So here you can see that it is going almost towards the 10 volt. Okay, so and then it's coming down. Okay, and this is the case of when we are considering this R1 to be 80 volt, and this diode also has a breakdown of around 6.3. so I have considered this one, this around 6.21 basically. So it is very close to it's close to the one that we have done the calculation. And if you see the this voltage also, it is very close to I should say that it's very close to 10 volt, around 9.8. so it's approximately the same. Okay, so now we can see the plot the diode current, the current flowing through this diode, and just see this behavior. So this axis, this y-axis is giving the current. So this current you can see is maximum when this is at peak, right? The B rectified is at peaked. Okay, okay, just let's name this node so that it becomes easier to follow. So you can see here it is going close to around this peak current, it is going through around minus 45. Okay, so which is of course lesser than the minus 50. The 50 is the maximum one. So and let's change this value to maybe of course 500. Okay, okay, so so now we can see this waveform, right? So if I make this, so this is my 500 ohms, so you can see this ripple, and if I change this value to be 1 kilo ohms, and if we just run the simulation again, so we can hardly see that this rectified ripple voltage is varying. So even though it may be varying, but very minorly. And I can make it this one to be around again 300. Okay, so 300, so still it's fine, it's still flat, and still the variation here is not significant, it's very small. So that means this ripple is defined by this resistance and this one. But of course, if I change this value, you'll observe if I make it maybe 120 larger, you will see that the ripple voltage is varying, right? Ripple voltage is varying. Okay, let's make it again 80. Okay, and now if I make this one smaller, 250 maybe, so my value is around 278. So you can see that this diode is now out of the breakdown region. So you can see that especially when it is at lower value, it's not going in the breakdown region. When it is at higher value, it is going in the breakdown region. When the rectified is output is at minimum value, it is going out of the breakdown region. Of course, you can plot the current now again. So you can see here that during this region, my Zener current is becoming almost zero. Okay, so that means this is going out of the breakdown region. And as I was mentioning, that in this case my ZK, we should make it around 0.2 milliampere. So of course, so this is 250, and if I slightly increase to 260 maybe, so you can see that there is a slight increase in the, now it is there is this diode current. Okay, and of course if I make it maybe 270 something like that, so you can see that there is, now it has slightly increased, right? So now in this case it is around okay, so it has started to 0.6 microampere. Okay, so although not that the values that we are getting here may not be same as the theoretical calculation, but we know that these values are not very far, right? So we have got a 278, but yeah, in this simulation it may be not 278, it may be little lesser than 270, where it is reaching 0.2. You can exactly find it out. So there is a slight variation in the values, but more or less this is not very far than what we have theoretically estimated. Okay, yeah. Okay, so with this we will end the discussion on the voltage regulation by the Zener diode.